Hello friends, welcome back. Did you have fun being a detective and cracking the code? I'm sure most of you did crack the code. Did you also guess then what would be our topic for today? Yes, it is number systems. Number systems is a very important topic not only for mathematics but also for computers, coding, and especially our journey of IoT, Internet of Things. So stay tuned through the video and let's get right into it. So why are zeros and ones so important? As much as they might look very simple, zeros and ones together are really very powerful. They can be used to give a lot of useful messages in our day-to-day life. Let's see something. 0 and 1, let's take some examples. A yes, a no, thumbs up, thumbs down can be represented by 1, 0. Similarly, up, down, correct, wrong, happy, sad, a day or a night, maybe brightness and darkness, all can be represented by 1 or 0. See the fun? Any situation or event which has two clear options can be easily represented by only one communication language, the language of 1 and 0. We know it is binary. Now, let's relate it to our IoT discussion thus far, because that's what we are doing this and understanding binary, right? Okay, so here goes. Recap on the IoT system. Similar to a human brain, in IoT system there is a microcontroller, and similar to the human ability of the senses, the 5 senses, there are sensors. Now these devices, microcontroller and sensors, are basically electrical devices. Sensors sense a property like temperature and sends an electrical signal like voltage to the microcontroller. The microcontroller needs to detect this signal, count the value, then store it as a number, so that later it can use it for any mathematical calculation. It's something like this. So exchange of information with the electrical signals of voltage and current, and you power it by something like a battery, right? Now, how do you count? For example, the microcontroller is basically an electrical device, and so it can determine the presence or absence of electricity easily, right? So we can say that a presence of electricity, a voltage or a current, can be termed as 1, and then an absence can be 0. So we can clearly represent yes or no in voltage. Right? This is a very reliable definition for counting, really, since there cannot be any mistake in measuring a presence of voltage. It is either there and so it's 1, or it is just not there, so it's a 0. Simple. So the best way, again, now that we can detect ones and zeros, the best way to store a number is in ones and zeros, which is the binary system that we already learned. Now, if we are not sure that we want to store the numbers in binary because we can detect ones and zeros, how could we store these ones and zeros? Well, since our microcontrollers are electrical devices, the best way to store them would be by using electricity. Now, how do we do that? Let's take a daily life example. Can we remember something that we do in daily life? The switches which light our bulbs? Here they are. Now see a switch on the wall like this. What do? The light is off, so it's a 0. We press the switch and the light is on. We toggle the switch, the bulb gets off. So a switch along with the electricity, a bulb here, can be used to represent 0 and 1. Now let's apply this switch principle to our microcontroller. Of course, we can't use this switch as it is like a button, but we would have something similar as an electrical switch. Let's find out. In fact, microcontrollers are made of thousands of switches, electronic switches, which can be kept on by applying electric current or voltage, or they can be made off by removing the current or voltage. These electronic switches are known as transistors. A transistor looks something like this. Just remember, the size shown here is way too big. We can use this in our electrical circuits, but when it is used in microcontrollers, they are really, really tiny. So that thousands of these transistors can fit into a small microcontroller chip. Now, this transistor is similar to our switch. It has an incoming input voltage pin like a switch has input voltage. You have to have an output voltage once the switch is actually made on. So you have an output voltage pin which currently doesn't have any output, right? And then to toggle the switch on the button, we need an electrical button, that is the electrical trigger signal pin in the middle. Now currently there is no output voltage, so a 0 is stored in this transistor as a switch. Now let's give it a trigger. So the trigger, small trigger signal, we call it as a trigger signal or the bias signal. Once it's given and you want to store 1, what happens? The transistor switches and gives an output voltage at the output pin, and it stores it, and that's a 1. So that's the way a transistor works. And there are millions of them, thousands of them into the microcontroller. Okay, so with the importance of ones and zeros understood, let's move on further. Remember our Beer Detective Crack the Code game? The numbers used by the challenger, 0 to 9, are part of decimal number system, and the ones used in the secret code, the zeros and 1 code, make up a binary number system. Let's discuss them in detail now. Okay, so keep an eye on the left hand side first. This is our day-to-day system, and because we have 10 symbols starting from 0, we will see how it works. Okay, so keep an eye on the left. So this is how the numbers start: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That was easy. We had 10 symbols, we counted 10 from 0 to 9, and it was easy. What next? Now if we have to count further, let's try to count. What would we do? We don't have any more symbols, so we'll have to reuse those symbols. So how do we do that? See here. So what happens? The 9 changes to 0 again. We have to use the new symbol 0, and because the 9 shifted to 0, we have to indicate somewhere that we have completed a counting of 0 to 9, which is 10 numbers, and so on the left hand side we added a number and said 1. What does 1 indicate? That once we have completed a counting on the right hand side of 0 to 9, that is 10 symbols. See on the right hand side what happens. Let's do it the similar way. Okay, so see what happened? 0 and 1 count. Can we go to 2, 3? No, we don't have those symbols. So if we have to further count, what happens? Exactly the same that happened on the left. See there? The 1 changed to 0 because we have no other symbol. But now, because we had counted 0 and 1 and we did 0 again, we have to indicate that somewhere. So on the left, we added a digit 1. So 1 indicates that we have completed a cycle on the right hand side, and the cycle was counting 2, 0 and 1, right? Remember this. Now let's see what happens further. So let's continue counting from 1, 0 and see on the left. Now we will complete our counting on the left hand side and then see how it relates to the right hand side. Okay, so keep an eye on the left hand side. Okay, so here it is. Again we completed the cycle 0 to 9. Again what happened? After 9 we have to go to the 0. But now because we went to the 0 again, we have to indicate somewhere we have done it 2 times over. So the 1 on the left hand side now became 2, which tells we have counted 0 to 9, which is 10 twice over. So do you realize something? Onto the first right hand side column, we change for every count. The symbol changes for every count. The same symbols are used onto the second column on the left hand side, but that symbol changes only once every 10 counts. So it is a bit of a bigger number. So every time we go to the left, there is a bigger number. Let's continue to see a pattern. What happens? So now we count again the same thing. We counted one more time. Again we got a 3 on the left. So now it tells you have done the counting 3 times. The 10 counts have been done 3 times, 0 to 9, right? Now similarly, if you just proceed, it will happen 4 0, 5 0, 6 0, 7 0, 8 0, 9 0. So that tells us we have counted the tens on the right hand side 9 times over. Now there is something interesting that will happen again. So let's do this and count again. So now again we counted from 0 to 9 and we come to 9 9. Now what? The first 9 on the right will go to 0. But what about our second 9 on the left? Even we no longer have any more symbols. So we would again have to change that to 0. And then what do? Perfect. So we know every time we finish our digits, finish our symbols, we add a new digit onto the left hand side. So this is what would happen. This goes to 0. This changes to 0. And now we add 1. Let's get our concepts complete now. So if we continue the way we continued early, we are going to reach a 9 onto the right two digits. And what would happen? Think, you guessed it right. The 9 nines would become 0 zeros and the 1 would have to become 2. So now we have know that it has completed the round of 10 times and those 10 times over to give you a 200. Perfect. Now, since we understand completely on the left hand side, our system of 10 symbols works. Let's go to the right hand side again. What happens? Now let's start incrementing it on the right hand side. This is going to be quick because we only have 0 and 1. So we incremented 1. So what happens? 1, 1. Now let's do increment one more time. Now what happened? This changed to 0. Now this has to go onto the left hand side. This changed to 0 because we have no other symbol. We have to reset and we have to go back to 0. So what do? We add a 1. See how quickly we reached 1, 0, 0? The first one on the right hand side came to 0 and told the left hand side, you have to go increment one more. Now because it was already a 1 there, it became a 0 and added another digit onto the left hand side. So we have 1, 0, 0. Now let's go a bit further. Add one more digit. Simple. Just 1 and it becomes 1, 0, 1. Now you add it, so this becomes a 0. It pushes a 1 here. Now since 1 is allowed, we don't have to push another thing to the left. So it's 1, 1, 0. The third one should be simple. 1, 1, 1. So we are all ones. Now it is clear. If we have to increment more, we have no more symbol and we have to go back to 0 as a new symbol again. So what do? You got it. Put another digit on the left. Yes. So see how quickly the system on the right increase the number of digits because you have less symbols. So when there are a number of symbols, different distinct symbols are less, the number of digits as you count increase faster. Whereas on the left hand side, when we had less number of symbols, the number of digits keep on adding a bit slow. Remember this. Okay, so let's consider a 5-digit number with symbols 0 to 9. This is our first system, our challenger system. Okay, so let's take a random number 57623 and this is the number 5 digits. Okay, now each and every of digits we have to call it by a place number so that we can refer to it. Now since we have the numbers from 0 to 9, let's call the first place as 0. We normally count 1, 2, 3, 4, but in here we have to give a name to a place and we have 10 symbols 0 to 9. So let's start with the 0. So the rightmost is 0 and then 1, 2, 3, 4, right? So that we can refer to it. So remember, we saw into the video earlier that each place changes after a particular count. So the rightmost place here, it changes after every one count. Now once we complete 10 counts here, this digit changes here. So this digit changes every 10 counts. Now remember, once this gets completed 10 times 0 to 9, then this gets changed, which means this changed 10 times 10, which is 100. Similarly, this is after 1000, 10 times 100, and this is 10 times 1000. So this we call as the value of this digit, because this changes slower than this changes slower than this. So number 3, the place value 2 changes slower than place value 1, which changes slower than place value 0. Okay, right. So now what happens? What we spoke, we are writing it here. So place value 1 multiplied by 10 gives you the place value of the second place, place 1. Again multiplied by 10 gives you the next place value. Again multiplied by 10 gives you the next place value. Again multiplied by 10 gives you the next place value. Keep this in mind. Remember how the number system works. So there's a place and there's a value to every place, and every place changes exactly with the same multiplication of 10, right? For some people, some of you who have learned exponential, it's not important for those people who don't understand, but if you have learned, 1, 10, 100, 1000, 10,000 can be written as 10 raised to 0, 10 raised to 1, 10 raised to 2, 10 raised to 3, and 10 raised to 4. See something interesting? 10 raised to 0 and the exponent here, 0, is the name of the place here. 1 is the name of the place here. 4 is the name of the place here. So, if you want to find the value of a particular place, if you keep on adding numbers here, just write 10 and just write an exponent of that place once you start the place numbering with 0, right? So this is the numbering system that we use daily, and this is how it is used. Now, if we are clear about the left hand side, let's go to the right hand side. Do exactly the same thing, but with only two symbols, 0 and 1. Okay, and take a random number, 1, 0, 0, 1, 1. We can only use a number with ones and zeros. Again, give the places the same name, 0, 1, 2, 3, 4, starting with 0. So there are 5 digits, 5 place numbers starting from 0 up to 4. Interestingly, do you remember how we did the counting? On the first place on the right side, we only changed, every time we changed, we counted 1. It changed every time we counted 1, the digit and the symbol changed. So the value here is 1. The second column changed after every time we counted 2 here. Similar to every time we counted 10 here, 0 to 9. Here we counted only 0 and 1 and this changed. Similarly, when we do it twice here, it changes to 4. We will get this more clear if you want to when we do the multiplication later. So 1, 10, 100, 1000, 10,000. Similarly, we multiply here because we have only two symbols. Each value would change by multiplying it by 2. The same as because we had 10 symbols here, we multiplied it by values of 10. We do it by values of 2. So 1 into 2 is 2. 2 multiplied by 2 is 4. 4 multiplied by 2 is 8. And 8 multiplied by 2 is 16. So now for every of this place, we have a value. Value means after how many counts does the symbol at this place change. So symbol at this place changes when you count 2. Symbol at this place changes when you count 4. And this when you count 8s, and this when you count 16s, and this will continue. Guess something? What would be the next digits? 16 multiplied by 2, 32. And 32 multiplied by 2, 64. And this can go on, right? Again, this can also be written as an exponent for people who understand exponent raised to. So this is 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4. And again 0, 1, 2, 3, 4 at the top are the place numbers. So if we want to find a value at place number 5, we have to write 2 raised to 5. And what does that mean? Multiply 2 5 times. 2 multiplied by 2 multiplied by 2 multiplied by 2 multiplied by 2. That gives you 32. Right? So once we compare this and see this, let's see what we got. So on the left hand side, this is a counting system, a numerical counting system of 10 different symbols, and each place value is a multiple of 10. We multiply by 10 to get the next place value. This system is known as a decimal system. Deci means 10. Decimal system, or we also call it as a base 10 system. The base we start is a 10. So it is a base 10 system. Any guesses what could this be now on the right hand side? Because we use only two symbols and each place value is a multiple of 2, multiplication of 2, we call it binary. Binary is 2, 0 or 1, and hence we call it as a base 2 system. Right? Okay. So that's it for today. Hope you had fun learning about numerical systems. Thanks for watching and see you soon.